everybody, this is Ms. Williams. We're going to start a new unit on exponential and log unit, and this is the first video of this unit. First, let's talk about what exponential functions are. They're different than any other kind of function that we have encountered because the independent variable, the x variable, is actually going to be in the exponent. Here's an example of one of those. F of x is equal to 2 to the x power. 2 is your base, and the independent variable, the x, is up in the exponent. Alright, let's look at a graph of this function by plotting some points. So here's your coordinate plane, and if I was to make a t-chart, if you plug in 3 to the x spot, you get 2 to the third power. 2 times 2 is 4 times 2 is 8. Okay, so if I plotted that point, it would be way up here. Over 3 up 8. Alright, what if I plugged in 2? 2 squared. 2 squared is 4, so plot that point, be right there. If I plugged in 1, 2 to the first power is 2. So there's that point. Anything to the 0 power, so 2 to the 0 power is 1, so it's right there. Sorry about that, they're having soccer conditioning outside. Then we get into negative exponents. Remember, negative exponents mean you bring it to the bottom. We just finished going over that. Okay, so if I put in negative 1, I get a half. If I put in negative 2, I get 1/4. If I put in negative 3, I get 1/8. Okay. Important to note right here that this graph will never cross the x-axis. It'll just keep getting smaller and smaller, 1/8, and then 1/16, and then 1/32, but it'll never actually get to 0. Okay? Connect your dots, make your line. There's your function. All right? So here's the general formula for an exponential function. F of x is equal to a times b to the x power, where a is called the initial value, so whatever's in the a spot is called the initial value, whatever's in the b spot is called the growth rate, and then x is just going to be your variable every time. Alright, so let's look at some of these graphs. Let's pretend that I just make a be 1, and I'm going to change the value of b to see what happens. So here was the graph from the previous problem. Okay, f of x equals 2x. What would f of x equals 5x, 5 to the x power, look like? Well, it kind of looks like the same shape, but if you notice, it goes up a little faster. Okay, and then finally f of x equals 10 to the x power. Kind of the same shape, but again, it looks like it's closer to the y-axis, which means it's going to be going up faster. No matter what we make b, the initial value of 1 will stay the same. Here, it's called the initial value because it's where it crosses the y-axis. Alright, it's Coach Hodge outside. What do you notice about the graphs? As the b gets bigger, the graph goes up faster, and that's why it's called the growth rate. Alright. There are things called exponential growth, and then there are exponential decays. So an exponential growth is when it goes up forever and ever. And this is the equation of that graph. F of x equals 3 times 2 to the x power. And an exponential decay is when it goes down and it bottoms out. It can't go down forever. It just goes down and bottoms out towards something. And the equation for this function is f of x equals 3 times 0.5 to the x power. So this is an important thing to remember, that if you have an equation of an exponential growth or decay, you can tell which one it is by just looking at the equation. A growth function must have a number in the b spot that is greater than 1. If you want it to be an exponential decay, then you will need a number in the b spot that is between 0 and 1. It can't be negative, and it can't be a number 1, but it can be between 0 and 1. So 0.5 is why that's an exponential decay. All right. Transformations is something we also covered on our last test. All the transformations that you learned apply to all functions. So what would the graph, if this is my original function, y equals 2 to the x power, what would y equals 2 to the x power plus 3 look like? Well, that plus 3 at the end, when you add and subtract at the end of it, outside the grouping symbols, it actually shifts it up 3. So our original function's over here to the left, written in blue, and then you just shift it up 3. So instead of going through at the 1, it's going to go through at the 4. Same shape. Alright, what about negative 2 to the x power plus 1? So again, the plus 1 is going to make it go up, and the negative in front is going to reflect it. Alright, reflect it over the x-axis. So again, the blue is your original function, and they have flipped it and moved it. And then finally, how do you shift it left and right? Well, your grouping symbols are up here in your exponent. Even though you don't see parentheses, it's still grouped together in the exponent. All right? So a -2 up in the exponent is actually going to move it to the right, and then the -1 is going to move it down. So your original function moved down 1 and to the right 2. All right? All right. So when are we ever going to use this, right? It's what you're always asking, so let's do a couple real world problems. Here's our formula again. F of x equals a times b to the x power. A is the initial, b is the growth rate. So if I had a question, it says Melissa bought a house for $100,000. It is known that the house in this area increased in value at a rate of 3% per year. How much will the house be worth in 5 years? So what's my initial value? $100,000. That's how much she bought the house for. All right, this is the important part. Her growth rate is actually 103%. Her house is worth everything it was last year. Everything means 100% plus an additional 3%. 100 plus the 3 is 103%. And then remember, changing percents to decimals, move the decimal place 2 spots. So our growth rate is actually going to be 1.03. And then our variable, we want to know how much it'll be worth in 5 years. So 100,000 times 1.03 to the 5th power gives us $115,927.40 is what our house would be worth. Okay, let's talk about a decay one. Becky bought stereo equipment for $1,500. The equipment loses value at a rate of 12% per year. How much can she sell her used equipment for 3 years later? So her initial value, let me go back. There's your equation. A is the initial value, B is the growth rate. Her initial value is $1,500. Now, her growth rate here is only 88%. Why? It's because her equipment is losing value. She doesn't even have everything she started with. All right? She is losing 12% a year, so she will still have 88% of her value left. So to get a decay, you have to take what you started with, which is 100% of your stuff, and subtract off the percentage that you're losing, which means you have an 88% growth rate. And here we're looking for 3 years, so that's going to be what goes in the x spot. So 1,500 times 0.88 to the 3rd power. Her equipment after 3 years is only going to be worth $1,022.21. All right, we'll work some more on these problems when you get to class. Hope everyone has a good night. Talk to you soon.